Hello, everyone. My name is Le, and I'm a graduating PhD student from UIUC. Today, I'm excited to tell you about Cameo, a new fine-grained string processing system that achieves both high resource utilization and performance isolation. This is a joint work with my collaborators, Shivaram, indeed my advisor, Luo, and Rahul. Distributed string processing systems are widely applied to areas such as social networks, cloud management, web applications, edge, and IoT infrastructures. They're typically used for time-sensitive tasks such as event detection, real-time data analysis, and prediction. These systems consume large volume real-time data. The data input are typically unpredictable temporarily across time and spatially across different sources. Meanwhile, user queries come with different performance expectations. Oftentimes, these queries become jobs running simultaneously in consolidated cluster or service, meaning that resources are shared and explicitly managed by users or service providers. For example, in a shared string processing cluster, we could have two types of jobs that coexist. Latency-sensitive jobs that typically connect to user dashboard or ad campaigns that associate with tight latency constraint, and bulk analytics jobs that could represent social media streams being processed into longer-term analytics with aggregation windows. Resource management for string processing applications is notoriously difficult as cloud practitioners have to balance the trade-off between application performance and resource utilization. On one hand, for users who deploy a performance-critical job that consumes data input that is potentially unpredictable, it is safe to over-provision and opt for full resource isolation where operators are assigned dedicated resources. This ensured unaffected performance under workload peaks, but could result in severe resource underutilization that generate high costs to the users. On the other hand, for users who have limited budget or resource and aim for higher resource utilization, they could choose to multiplex multiple jobs on shared resources. This approach uses resource efficiently but could lead to compromised performance such as high processing latency. We come to realize that to achieve the best of both worlds, there's a need to design a new string processing system that allows fine-grained resource sharing with performance isolation. Therefore, we built Cameo, a data-driven, fine-grained operator scheduling for string processing systems. Cameo is based on streaming runtime built on top of virtual actor framework, or LINX. Different from the state-of-the-art string processing systems, it achieves high utilization by adopting an event-driven architecture by treating operator invocations as serverless functions. Here, resources are only provisioned to operators that receive messages. Meanwhile, it enables fine-grained scheduling by identifying and prioritizing operator invocations that requires immediate handling. Cameo achieves data-driven, fine-grained operator scheduling through Cameo strategy and Cameo mechanism. We first discuss Cameo strategy. Coming back to our example before, say that we receive four messages, M1 to M4, where M1 and M3 target operator 1 that performs window aggregation with longer latency target, while M2 and M4 target operator 2 that triggers immediately with shorter latency target. We use red lines to mark the deadlines before which messages need to complete without violating performance target. With M1 to M4 arrives in order, M2 and M4 are required to target closer deadlines. We could see that the best schedule requires M2 and M4 to be scheduled before M1 and M3 to avoid any performance target violation. This can be achieved by ordering pending messages based on their deadlines of executions. By default, for a scheduler that has no awareness of any job-specific information, it will schedule messages based on their arrival order, meaning that the deadlines are presumed to be the arrival time. As the scheduler is completely unaware of performance target, M2 and M4 both fail their deadlines, which is why they're shown in red. The scheduler could improve its schedule when it starts to consider data flow DAG and latency constraint. In our case, it provides preliminary estimation of message deadlines, assuming every message triggers its target operator. With the new deadlines, the scheduler would prioritize M2 and M4 due to their shorter deadlines, which reduce the number of violations in our example. The scheduler can further discover opportunities of optimizations by further exploiting query semantics. Query semantics helps scheduler to identify whether or when the certain message triggers target operator. In our case, knowing that messages target window aggregation operator, which is M1 and M3 here, helps scheduler to delay messages cooperatively in order to prioritize messages that have tight deadlines. This further improves our scheduling result and preventing all violations. In reality, for a data flow that have many operators forming a DAG, messages that target on different data flow and different stages of the data flow can appear at the system at the same time. For any given message in the data flow, Cameo estimates the output that will be affected by this message and the deadline for result to be produced without violating latency target. In particular, this calculation requires Cameo to keep track of latency requirement for the job that a message belongs to and to have the ability to analyze the earliest time of the next result to be ready who will be first influenced by this message, which we call frontier time. The deadline calculation also requires scheduler to be able to estimate the execution cost of this message, as well as execution cost of its potential critical path. We realize that this process requires scheduler to be able to interpret query semantics of each individual job while also track dynamic information such as execution cost and timestamp of each message. Cameo adopts a simple design where it does not keep this information in a central place and instead relays this information with message using priority context, and we will discuss this next. Now we have introduced Cameo strategy. We will discuss the internal scheduling mechanism adopted by Cameo. In Cameo, user jobs are translated to data flow plans and then being mapped to ordinance actors before scheduled to each machine. Within each machine, Cameo uses a priority-based scheduler that organizes pending operators based on their priorities. Operator priorities are also updated with arriving messages. Within each operator, Cameo scheduler organizes all pending messages based on their global and operator local priorities. The most highly prioritized message determines the priority of its operator. Cameo's design spans across two layers. In streaming runtime, Cameo exposes priority generation API that allows custom scheduling strategy to generate and modify priority for each message. Inside Actor Framework, Cameo Scheduler dynamically orders messages based on message priority while remaining stateless to query specific information. For a pair of highlighted communicating operators here, we show how this process works as follows. For all requests sent out from the source operator, Cameo exposes API function that allows custom scheduling strategy to specify how priority should be generated. Message priority are written in the form of priority context and attached as a metadata of the data message. Once the message is dispatched, Cameo Scheduler schedules messages based on priorities written in the metadata. This means Cameo Scheduler stays transparent to the user level information, such as performance targets and query semantics. This design helps Cameo Scheduler to remain stateless and efficient when many actors are being scheduled or actors are reallocated dynamically. If a downstream message is triggered at a target operator, Cameo uses the scheduling API to modify and update priority context. The new priority context will continue to propagate downstream. Cameo also uses another type of context to backpropagate information, such as performance metrics upstream. For the details of scheduling context and scheduling API, we encourage the viewers to read our paper. We show how Cameo affects operator scheduling within single application. Cameo can shorten query latency by around 3 times compared to default FIFO scheduling. Here we plot operator schedule in a timeline. While x-axis corresponds to the time of the message being processed, the y-axis corresponds to the operator that execute these messages. We draw a line that separates messages that target different output. Specifically, all execution that falls on the left side of the red line influence the first result, and all execution on the right side contributes to the next result. As we can see, Cameo effectively reduced query latency by identifying and prioritizing operators that target the immediate result and preventing operators that target later result from occupying resource first. Cameo can be used to support other performance objectives beyond latency through programmable scheduling API. Here we show that Cameo can be used to implement token-based rate control mechanism. Here, three identical jobs receive 12, 24, 24 tokens respectively at each data source. As you could see, Cameo prioritized token input messages and all downstream traffic generated by these messages. When three jobs coexist, the throughput is split into 20, 40, and 40% respectively. This shows Cameo successfully translate token allocation to throughput shares. In our paper, we discuss in detail how Cameos infers data flow output based on input messages. We also demonstrate how user could use Cameo to implement scheduling strategy by steps. And we further show that Cameo improves query latencies as well as stabilizes latency fluctuations significantly in multi-tenant setting. As a conclusion, we propose Cameo, a fine-grained scheduling scheme for serverless, event-driven stream processing services that achieves both high utilization and controllable performance. Thanks for listening, and feel free to contact us if you have any questions.